So it's time to go through questions and examples. There are quite a few examples that we're going to go through in this lesson. And so we're going to be taking a look at different shapes of charges and how we can calculate the total electric field at a point P away from that charged object. So depending on the object, depending on where it's placed on your coordinate system, those different types of things can either make your life really easy or really hard when it comes to integrating. So this only comes with more practice and being able to think clearly about these questions. But do the practice. If you have any questions, definitely speak to myself, Professor Saini, or the TAs so that you can get some help to guide you along with these examples. In this example, charge Q is uniformly distributed over a length of L. We're trying to calculate the electric field at a point P, a distance r away on an axis going through the middle of the line. So a diagram was presented to us in the example, but I think the first step to any of these problems involves drawing and labeling a diagram to the best of our ability. So what I'm going to do is redraw that diagram and label every part of it. Since so much of this involves being able to pick a coordinate system, pick an origin point, and also look at symmetry, being able to draw a really good diagram and being able to visualize this is extremely important. So what was given to us was something like this. We had the y-axis and also some sort of, let's just say, a thin straight rod that we can consider a line. So let's point to this and say this is a straight, thin rod of uniform, linear charge density. So what was important about linear charge density? We know it's rho L. And we're given that a charge Q is uniformly distributed over a length L. So we're given the total charge and the total length, which means rho L is equal to Q over L. So that means we have a constant for our linear charge density, and that remains. We can move on, and it says the electric field at a point P, a distance r away on an axis going through the middle of the line. So this middle of the line was drawn and given to us and shown as something like this. So the x-axis goes straight through our blue rod, and there's going to be a point P somewhere here. So we'll call this P. And this point P is going to be a distance r. Let's make this clearer. R away from the y-axis. What else do we know? We know that the total length of this rod is L. So what does this tell us about the position of the ends of the rod? If this is 0, that means this is positive L over 2, and this is negative L over 2. Now the next thing we want to look at is, so let's just draw a couple of comments here, or write a couple of comments. So we divide L, the total length, into baby lengths, dl. So if I divide this tiny piece or if I divide L into this tiny piece and call this dl, then I also know that this dl is going to have a charge dq associated with it. And this charge dq is going to be directly a certain distance away from P, and also have a dE. So I call this R, I call this R hat for the direct distance from dl to a point P. Is there anything else we can glean from this diagram? Probably this being some sort of theta, and the fact that this can be broken down into its component forms, and it's also known as theta. So then these would both be right angle triangles. The next thing I want to take a look at is here. So the height is y. And consider this y. And this distance r won't change. So x will definitely always be equal to r, because p is a horizontal distance of r away from the y-axis permanently. So then the next step for us is to try and find dq and dE. So I know dq because this is linear. It's going to be rho L dl. So I already know rho L from here. We already said rho L is equal to Q over L. So, but rho L is equal to Q over L. And dl, as we know, is simply, if you think about it, dl is the change in length, but here I have the y-axis, so isn't it exactly the same as the change in y? So dl is equal to the change in y dy. So just remember, we always have to change our differential elements back into something that we can integrate, and we can integrate with respect to x and y here, so we want to change dl to dy. So then dq is now equal to Q over L dy. Okay, so we now have dq, and now we have to figure out dE. But we also know when we take a look at dE that it's not a straight line. It is a straight line. It's not going in the x direction and it's not going in the y direction, but actually a combination. So we have to do component analysis for dE. So dE was in red, so I'll just copy this here. Let's see, like that. This was dE, and this was point P. So that's just blowing up the diagram over here. It means that we have dEx going this way and dEy going down. And of course we have an angle theta. So then one thing we have to look at when we're looking at component analysis is this r. So when I'm taking a look at r, I know that r here, or dE, is going to be equal to some sort of k dq over r squared in the r hat direction. So I need a way to analyze this r hat as well, and the r hat is in the same direction as dE. So let's try and analyze this. We have r hat being equal to a certain x distance being traveled in the x direction. So we have an x distance traveled in an x direction, and here we have a negative negative y direction, negative y value, because it's going down, over the square root of x squared plus y squared. Okay, so here, if this is new to you, simply, if you have a vector and you want to try and figure out the unit vector, then it would be the individual components divided by the total length of that vector. So this is pretty much the same thing. R is defined by two steps. It's defined by a step in the x direction and a step in the y direction, and you're dividing it by the total length of R. So if you wanted just Rx, which is really important, you would have the x direction over the square root of x squared plus y squared in the x direction. And if you wanted the y direction, you would have y over the square root of x squared plus y squared in the y direction. But we know that the y direction is down, so that means this is negative y. We know that the x direction is towards the right and positive, so we know this is positive x in the x direction. So the next question is whether we can simplify this. So can we simplify Rx and Ry just so that we can do our calculations? And we can. Let's just draw another triangle. So we have this from DE. Why don't we draw the orange one here? So we have, let's see this. So we also have theta, but now we have capital R being x, we have y over here, and we have r squared, the square root of r squared plus y squared. So when we're talking about the directions, especially for the unit vector, we can say that this is simply going to be, let's just rewrite this. Rx goes in the x direction, so that means it's r in the x direction, divided by the square root of r squared plus y squared. Ry is simply going to be negative y over the square root of r squared plus y squared in the y direction. So now we have our simplified forms that we want to use, and we can find dE. So dE is then equal to k dq over r squared times r hat. But r hat is defined as these two, so we can say k dq over r squared and write r hat as rx, ry in each direction. So we want r, so try rewriting this, r over the square root of r squared plus y squared, and negative y over the square root of r squared plus y squared. In other words, what we can do is simplify this even further. dE is equal to, just keep in mind, this r is equal to this. So let's rewrite this entirely. We now have dE is equal to k dq over the square root of r squared plus y squared squared is going to be equal to r squared plus y squared, but also you have this square root of r squared plus y squared that you can take out. So that means I have k dq over the square root of r squared plus y squared squared cubed. So I have this cubed in the direction of r negative y. Let's simplify this further. dE is equal to k dq over r squared plus y squared to the power of 3 over 2 in the direction of r negative y. And all this really means is that in the x direction, you're moving over r steps and you're moving down y steps in order to get to your r vector, or your r. Like this. Okay, so now this is our component form of our differential electric field element, and the next step is to try and figure out our integration. So now let's solve for the electric field. And now we do have to take a look at symmetry. So I know here we have the x and y component, but going back to the drawing, if I take a look at this point P, there is going to be a vertical contribution from all the charges. It's going to be a positive contribution from everything above 0 to L over 2 affecting point P, and there's going to be a negative contribution from 0 to negative L over 2 affecting point P. So to me, it seems like all of the forces from above and below are going to cancel out. So that means if we calculate the integral of dEy, it should come out to be 0. So by symmetry, the integral of dEy should be equal to 0. So we can say that the electric field E will solely come from the electric field calculations in the x direction. And that's what we're going to do here. We're going to solve for E, and we're going to make life easier by setting it equal to Ex. So now we can say E is equal to Ex, which is equal to the integral of dEx. So if I just want to take a look at dEx, dEx is equal to only the x component here, which means I have k dq, and I can take out the r in the x direction, divided by r squared plus y squared 3 over 2. And this is what we'll use for our integration. So E is equal to the integral, and once again, if I'm integrating, I have to integrate with respect to dq, and dq we already solved for. dq is equal to q over L dy. So let's rewrite this as KR dq is q over L dy. The answer is going to be in the x direction, and we have r squared plus y squared to the power of 3 over 2. One thing we're forgetting are the bounds. So when we take a look at the bounds, we're integrating with respect to dy. So that means the bounds are going to be from negative, they're going to be from negative L over 2 to L over 2. So then E is equal to, let's take out as many constants as we can. We have K R Q over L, is the integral of negative L over 2 to L over 2 of dy over let's see, r squared plus y squared to the power of 3 over 2. And the answer is in the x direction. So now we have an integral that takes us back to our calculus classes, and we have the integral of 1 over r squared plus y squared to the power of 3 over 2. In this case, we want to use trig substitution. So we know from our diagram that we've drawn here, this is, oops, don't know why I erased that. That is theta. So in this case, what we would want to do is write down the tangent of theta is equal to y over capital R. So that means I can rewrite this as y is equal to r tan theta. So if I take the derivative, once again, remember I'm using one of the tricks that we've done in previous calculus courses. So we're doing a substitution. So we take the derivative, and the derivative is going to be r secant squared theta, d theta. Okay, so that's one done. Next, I want to make a substitution. So let's say secant of theta is equal to hypotenuse over adjacent. If I take a look at this triangle again, the hypotenuse is r, and what was r again? R was r squared plus y squared, and adjacent is capital R. So I can rewrite this as the square root of r squared plus y squared is equal to r secant theta. So my goal now is that I've replaced this dy with this expression, r secant squared theta, d theta. I now have to find a way to replace this. So in order to replace that in terms of theta, we have a perfect setup here with r secant theta. If I cube this, which is the same as r squared plus y squared to the power of 3 over 2, I get r cubed secant cubed theta. So now I can replace the highlighted yellow part with this. Are we done? We're not done, because there's one thing we've forgotten to change, and it's these boundaries. So with these boundaries, we're just going to temporarily say that negative L over 2 is going to be changed to theta 1, and L over 2 is going to be changed to theta 2. So we're just going to leave it there for now, and then we'll be able to figure it out in a bit. So let's make our changes. We have E equals to K, capital RQ over L. The integral from theta 1 to theta 2 dy is now R secant squared theta d theta. Answer still in the x direction, haven't changed that. Divided by, we have R cubed secant cubed theta. Okay, so now I can simplify this further. It seems like I can take out the r's, so I have kr squared q divided by l r cubed. Integral theta 1 to theta 2 of secant squared theta divided by secant cubed theta. This is just 1 over secant theta d theta. Answer still in the x direction. E is now equal to kq divided by rl. So that constant has simplified itself. Now, secant of theta is 1 over cosine of theta. So if I have 1 over cosine of theta, then it's simply cosine of theta d theta in the x direction. So now this is a much easier integral to solve. We have E being equal to kq over capital R times L. And the integral of cosine of theta is positive sine theta. Theta 1, theta 2, in the x direction. So let's solve. This is sine of theta 2 minus sine of theta 1. And just remember, we haven't defined theta 1 or theta 2 yet, so we're going to have to do that next. So now let's take a look at theta 1 and theta 2. So if I take a look at the drawing from before, we had our length L. This was 0, this was positive L over 2, and this was negative L over 2. And we had our x-axis here. And that also means that at a point P, we have theta 1 and theta 2. So if I take a look here, when I'm at negative L over 2, I make an angle of theta 1. And this particular triangle, if I want sine of theta 1, this triangle gives me opposite. So this opposite is negative L over 2 over hypotenuse. And the hypotenuse is going to be, so this is always r, is going to be r squared plus negative, don't have enough space. This is going to be square root of r squared plus negative L over 2 squared. So this would be r squared plus negative L over 2 squared. And that gives us negative L over 2 divided by the square root of r squared plus L squared over 4. So that's our sine theta 1. What if I want to take a look at the boundary for L over 2? So we'll consider this orange. So that means I have theta 2 here, and this length is positive L over 2, and I have this being the square root of r squared plus positive L over 2 squared. So sine of theta 2 is equal to positive L over 2 divided by the square root of r squared plus L squared over 4. So now I figured out what sine theta 2 is equal to, and I've also figured out what sine theta 1 is equal to. And I can plug that in to my solution. And I have kq over r times L. Sine of theta 2 is L over 2. And the denominator is the same, so why don't we just do minus L over 2 divided by the square root of r squared plus L squared over 4 in the x direction. E is now kq. L over 2 plus L over 2 is L, so the L over L are going to cancel each other out. So that means I have kq over r. It's kq over r times the square root of r squared plus L squared over 4 in the x direction. And that is our answer for the electric field. So as you can see, we did a lot of work for this, and it's a lot more work than we do want to do. So we're going to learn an easier way later on, but like all things, we have to learn from scratch. So in order to calculate the electric field, these are the efforts we would have to go through. There's also another step you can perform just to verify your answer. It's to prove that EY is equal to 0. So just a few other comments. So what happens if your R value is a lot larger than your L value? So basically what this is saying is, what if your point P is really, really far away from your rod? So in this case, E is going to go towards 2k rho L over R in the x direction. Or it's going to be rho L. If you say k is equal to 1 over 4 pi epsilon naught, we get 2 pi epsilon naught R in the x direction. So try and think about why that is. All you have to do is do an analysis of these where L essentially goes to 0, so that you can figure that out. So in this example, there's a uniformly distributed charge that sits on a horizontal line of length L with linear charge density rho L equals rho naught. We want to calculate the electric field at point P, where P is a perpendicular distance r away from the horizontal axis, such that the line joining P with one end of the line makes an angle A, or alpha, with the other end of the line making an angle of beta. So I want to draw this diagram first. It's already given to us, but like I said, the first thing we want to do is label as much as we can on the diagram so that we can leverage different relationships. So let's draw and label the diagram. We know that there is some sort of horizontal line of length L, which we'll draw in blue. So that's the thing that holds the charge. And it's lying flat on some axis. So we'll call this axis X. The point P is a perpendicular distance away from the horizontal axis. So we're given a point P over here, and this point P is a distance capital R away from the x-axis, such that the line joining P with one end of the charged line makes an angle alpha. So let's do this in green. We're going to say that there is a starting point and an end point to this line. This creates beta, an angle beta, and this creates an angle alpha. So now the question comes from where we place the origin. Do we place it at this point here, or in the middle? So technically, it's a difficult choice, purely because looking at this, we can't cancel out anything vertically or horizontally, so we're stuck with calculating the contributions to electric field in both the horizontal and vertical directions. So in this case, why don't we just put, we'll just do some notes here. So no symmetry. So let's just choose middle of L. So L would be, this would be the total length. We're just going to choose the middle of L as our x, our y-axis. So that's our origin. And now we can look at our DE. So we have our total length. Similar to the previous problem, we want to see the contribution from tiny pieces of this length called DL, which in this case is simply dx. We want to see how it contributes to the electric field at point P. So this is going to be dE caused by some sort of dq at dl. Let's just write this separately. There's a d. There's still more to label. So we can say dl is a small length element on the x-axis. So we know dl is equal to dx, that we've discovered already, but we still have to write it down. It means this dx has a charge dq. dq is equal to the linear charge density times dl, but we're told over here that the charge density is rho naught. So we have rho L equals to rho naught. So dq is equal to rho naught dl is equal to dx. So we have rho naught dx. So we found our dq. Now we also have to express dE. So in this case, we have, let's see, we must find dE. So dE is going to be equal to k dq over r squared, r hat. We know dq is rho naught dx over r squared, r hat. So we have this, and right now we want to try and simplify it as much as possible so that we can solve for the integral of dE. So as an aside, let's start with this. And we want to look at symmetry and solve. So there is no symmetry, so we must solve EX and EY separately. So we're going to take a look at the X direction and then the Y direction. So now the problem comes with being able to figure out what dEx and dEy are. So we haven't really done any discussion about this, but that's where working it out on the side comes in handy. We already know dE is equal to all this, so dE is also equal to this. So we have in red what I've drawn above. This was dE. And that means this is dEx, and this is dEy. And there has to be some sort of angle theta here. And that angle theta, which we can call theta or phi, doesn't matter, that angle theta is going to be right here. So that means we actually have two triangles to look at. Once again, similar triangles. We have this triangle for dE and also the larger triangle from here, here, and here. This was point P, whereas this is point P in this diagram. We have right angles. This is theta. I know this is R. And this is where it gets tricky, because we're just going to come up with some sort of length value. So let's call this, let's call this L1. So then the distance here, because we can consider this to be x, we can call this L1 minus x with a distance of r, or a hypotenuse of r. So I hope this makes sense. There are two different triangles here, and we just kind of created some value here with respect to x, because we do have to integrate with respect to x at some point. So we now have L1 minus x at the bottom. And like I said, this is just a number. Now, if I take a look here, if I wanted to find dEx, dEx is simply dE, which is the hypotenuse, times the cosine of theta. And dEy is dE sine theta. So that means I can write this as dE cos theta and this as dE sine theta. And we already know what dE is, so we can write that out, and we can say dE x is equal to k dq over r squared, or essentially k rho naught. So we have k rho naught cos theta dx over r squared in not the r direction, but the x direction. And so now I want to be able to simplify this further. I know I have to integrate with respect to dx, but I'm stuck with this cosine of theta as well as this r squared. There's too many variables in here and no constants I can take out, so I need to be able to find a way to simplify this. So looking at my triangles again, I know that the sine of theta is going to be equal to, so over here, sine of theta is equal to capital R over little r. So little r is equal to capital R over sine of theta. So can I not replace little r here with capital R over sine theta squared? So why don't we do that? It means we have, so let's sub r equals to capital R over sine theta. At least it gives me another theta and gets rid of the little r. So I have dEx equals to k rho naught cos theta dx divided by r squared over sine squared theta. Okay, so I now have dEx being equal to k rho naught cos theta and what else do I have? dx over r squared, and this is equal to cosecant squared theta. So now at least I can take k rho naught and capital R squared out. I'm still stuck with this theta. So either I get rid of theta and I convert all of the thetas to dx, but at this point it's probably easier if I convert dx to theta because I have two thetas here. So why don't we see if there's another way to represent dx? And that means going back to our triangles to the right, and now I can say from here I have tangent, so following in black with the black triangle, I have tangent of theta is equal to opposite over adjacent. So that means I have let's see, L1 minus x equals to r over tan theta, or r over cotangent of theta. So what if I had d over dx? I'm going to integrate everything. Oops, I don't want to integrate over dx. I want to integrate over theta. So d over d theta of L1 minus x is equal to d over d theta of r cotangent of theta. Now this means the derivative of a constant is just 0, which is why this value actually did not matter whatsoever. We have 0 minus dx over d theta is equal to r cosecant squared, oops, not positive, r times the derivative of cotangent of theta is actually negative cosecant squared of theta, So now I have minus dx over d theta is equal to minus r cosecant squared theta. So the negatives cancel out and I get dx is equal to r cosecant squared theta d theta. Okay, so now I can replace my dx over here with what I've just discovered. I have dEx is equal to k rho naught cosine of theta times r cosecant squared of theta d theta divided by r squared cosecant squared theta. And thankfully, we can actually cancel these out and simplify our lives quite a bit. The r disappears at the top, and the bottom just becomes a singular r, which means I have dEx equals to k rho naught over r cos theta d theta. And now when I integrate, it's a lot easier. I can calculate Ex, and that's the integral of cos theta d theta. And the thing is, what the angles are, I do have an angle, and if I take a look up here, this angle theta is simply beta and alpha at different points in time, in space. So at the beginning of this rod, it has an angle of alpha, and at the end of this rod, it has an angle of beta. So all we have to do is just integrate from alpha to beta, and that means Ex is equal to k rho naught over r sine theta from alpha to beta, and we have Ex is equal to k rho naught over capital R sine beta minus sine alpha. Okay, so when done for the x direction, we still have to do the y direction, and it's literally the exact same thing. So now we can shorten up quite a bit of our process. We know that we're going to sub r equals to r over sine theta. We also know we're going to sub in dx is equal to r cosecant squared theta d theta. So it's dE sine theta, so dEy is equal to k rho naught sine theta dx over r squared. So the only difference here is just our sine theta. So we can just rewrite what we've done before, k rho naught sine theta times r cosecant squared theta d theta divided by r squared cosecant squared theta. Remember, these canceled, and all that's left is dEy equals to k rho naught over r sine theta d theta. This means I can integrate and get Ey is equal to k rho naught over r times the integral from alpha to beta of sine theta d theta. And Ey is equal to k rho naught over capital R negative cos theta from alpha to beta. Ey is equal to k rho naught over capital R. We have negative cosine of beta plus cosine of alpha. We can simplify that even more, or just make it easier to read. So we have cosine of alpha minus cosine of beta. Okay, so that was very tedious. We're still not done. We still have to represent we have to write out the total electric field. So therefore, the total electric field is going to be equal to K rho naught over R of, we have sine beta minus sine alpha in the x direction, plus we have cos alpha minus cos beta in the y direction. And that would be your final answer because the electric field is defined in both the x and y directions, and there's no way we can cancel out any one to make it more simple. In this example, charge is uniformly distributed over a ring of radius a, and we're trying to calculate the electric field at a height z above the center of the ring. So first thing, draw and label our diagram. So because this is in a 3D coordinate system, we have to be careful about where we're replacing things and where we're labeling. So it says charge is distributed uniformly over a ring of radius a. So we have a ring. And let's see, we have a ring, so try and make this a little bit more accurate. So something along these lines. The idea of a ring is that it's going to be still a line in a circle. So that means we have a very, very, very thin ring. And that ring has a radius of a. So I'll just draw this right now. Radius of a. The other thing is that we want to figure out the electric field at a height z above the center of the ring. So here's the center of the ring. And we're looking at a point P right above it. So that means we have to consider some piece or short segment of this ring and its contributions for the electric field at that point P. So why don't we cut out this section in red. And because it is a ring, we have dl over here. And from our polar coordinates, we know this is d phi. We also know that the radius, so that means the length of this, is a. So dl is the arc length, and it's a d phi. The other thing we know is that there's going to be a dq, a charge associated with this little baby step. So dq is going to be equal to some sort of linear charge density times dl. So we have dq being equal to rho naught a d phi. So what we can draw is this contribution acts on P, and then there's going to be some dE involved. Okay. So a couple of notes. We can take a look at symmetry. Along the x and y axes, it seems to me that because the z-axis is right in the center of this ring, there's going to be an equal contribution from the negative and positive y-axis, which can cancel out all the contributions from the y-axis. And there's also going to be an equal amount of contributions in the negative and positive x-axis. So those are going to cancel out too. So due to symmetry, all the DEs perpendicular to the z-axis will sum to 0. So in other words, DEX is equal to DEY, which is equal to 0. So we just need to look at DEZ. And considering DEZ there's going to be a contribution for DEZ around the entire ring, 360 degrees around it. It means that we must integrate phi from 0 to 2 pi. So that's all we know for now. Next, we want to be able to find DEZ. So we know DE is equal to K dq over r squared, r hat. And we know that r hat is simply going to be x, y, and z over the length of r. So if we want DEZ, we simply just need to grab the z component, which is going to be z over r. So we have k k dq over r squared, and we have z over r in the z direction. DEZ is equal to k z. dq was equal to rho naught a d phi. We're still in the z direction, divided by r cubed. Now the next thing is trying to figure out what r is. So when we take a look at r in this diagram is here in orange. R is a certain height z from the origin, and it's going to have a radius or a base of a. So I've drawn a too many times, it's confusing now. But a is here, so that's the bottom in red. So if I were to draw another triangle, it would be like this. We have r, z, and a. R is going to be the square root of a squared plus z squared. So that means I can rewrite this as DEZ is equal to k rho naught a z d phi in the z direction divided by the square root of a squared plus z squared cubed. So that means this would be cubed divided by 2. 3 over 2. So now I have my DEZ. I can now solve for E. So the first thing we note is that E is equal to EZ, which is equal to the integral from 0 to 2 pi of k rho naught a z d phi divided by a squared plus z squared, 3 over 2. In the z direction. And now my question to you is, what are constants and what aren't constants? So I'm integrating with respect to phi. There's no phi's anywhere, so everything is pretty much constant, and I can take it all out. So k is a constant, rho naught is a constant, a is a constant, z is a constant, and this a squared plus z squared to the power of 3 over 2 is also a constant. So the only thing left is just the integral from 0 to 2 pi d phi in the z direction. So E is equal to, when we integrate this, it's just phi from 0 to 2 pi, so it's 2 pi. We have 2 pi k rho naught a z divided by a squared plus z squared to the power of 3 over 2 in the direction of the z-axis. So as you can see, this question was a lot more straightforward and required a lot less work. And that's all because we were able to set dEx and dEy to 0, or else we would have to do all the calculations for all 3 directions. So in this example, the charge is distributed over the surface of a disk of radius a. We want to calculate the electric field at a height z above the center of the disk. So, similar to before, we're just going to draw and label our diagram. So this time we don't have a ring of radius a, we have a disk, so it's solid, of radius a. So I want to just draw in red, actually not in red, maybe in green. So we have this disk of radius a, and that means we're going to have little elements that are going to contribute to the electric field at some point P. So we'll keep P here. And it's a distance Z above the XY plane. Now what we want to look at is how we can simplify our calculations. And to simplify our calculations, we can realize that this flat disk is made up of a whole bunch of flat rings. So that means I might have a flat ring here. So let's see. So a flat ring here, and this flat ring is going to have some charge around it. So it's going to have a radius of r. So radius of r, and there's going to be a change dr. So it's going to be the thickness of that ring. So this is going to have a direct distance, which we can call d, and it'll form an angle theta. And dE can be represented like this. So then what kind of information can we get from this? First of all, let's always take a look at symmetry. So with this diagram here, I know that the contributions from the x and y direction are going to cancel out. So there's an equal amount of contribution from the positive and negative sides of the x-axis, and similarly with the y-axis. So by symmetry, the E field, due to the ring, is only along the z-axis, since the x and y components cancel out. The other thing we can look at is each mini-ring. Has a surface charge density of rho s being equal to rho naught with radius r. So we would have dq being equal to rho s ds. And ds. Now, in this case, because we have a ring, we can actually take a scissor, cut the ring, unfold it, and it just becomes a really long cylinder. So the total surface area is just going to be the area of that flat rectangle. Sorry, just to explain that one more time. If I have this ring like this, it's 2D. If I snip it here, I can unfold it into a long rectangle, and it's going to have a length of 2 pi r for the radius, and a thickness of dr. So that means ds is simply going to be 2 pi r dr. And that means dq is equal to 2 pi rho naught r dr. So now, the only thing we care about is dEz. So we know dE is only equal to dEz. So dEz is equal to k dq over r squared. And remember, it was only the z component of the unit vector r, so that means it's going to be z over r in the z direction. But there's something really important to understand here. The unit vector over here, k dq over r, this is not the radius of the disk. It's actually the distance from whatever we're looking at straight to the point. So we have to make sure we're using the correct quantity. So in this case, r is going to be equal to x, y, z, and d, which is the length of r. So now we can try and simplify this even more. We have dEz is equal to kz dq. dq is 2 pi rho naught r dr. And we have d cubed, but we can figure out d. d is simply r squared, the square root of r squared plus z squared. So if we cube that, we have r squared plus z squared to the power of 3 over 2. And this is all in the z direction. So with this, we can now solve for E. We have E equal to EZ, which is equal to, let's see what kind of values we can take out. We can certainly take out anything that doesn't have to do with R. So we have 2 pi kz rho naught. I think that's about it. Have the integral, and we know it's going to be from 0 to a, because dr is going to be from 0 to a of r over r squared plus z squared to the power of 3 over 2 dr in the z direction. So now it's time to look at trig substitution again. So we have, looking at this triangle here, the tangent of theta is equal to opposite over adjacent. So tangent of theta is equal to r over z. R is equal to z tan theta. And I want to be able to replace dr. So dr is equal to z secant squared theta d theta. Now we want secant of theta, which is, instead of opposite over adjacent, opposite over it's hypotenuse over adjacent because it's 1 over cosine theta. We have the hypotenuse being r squared plus z squared and adjacent being z. So that means I have the square root of r squared plus z squared is equal to z secant theta. I can cube that and I get r squared plus z squared to the power of 3 over 2 is equal to z cubed secant cubed theta. So now I can plug it all in. So I have replaced r with z tan theta. So let's highlight this. We can replace dr with this, and we can replace our entire denominator with that. The only thing we haven't looked at are the bounds, but we'll take a look at that after. All we're going to do for now is just say 0 is going to become theta 1, and a is going to become theta 2. And we'll take a look at that in a bit. So we have 2 pi kz rho naught times the integral of theta 1 to theta 2 z tan theta z secant squared theta d theta in the z direction divided by z cubed secant cubed theta. So from here, what I can see is that my secant squared gets rid of 2 of the secants from the bottom. I have 1, 2, 3 z's, so it's z cubed over z cubed. And I think that's as far as it gets. We have the integral from theta 1 to theta 2. Tangent of theta over secant of theta d theta in the z direction. E is equal to 2 pi k rho naught. So tangent is opposite over, tangent is sine over cosine, and then secant is 1 over cosine. So essentially, this is going to cancel out, so we have sine theta over cosine theta over 1 over cosine theta. So your cosines are going to cancel out and you end up with a sine. So now we have E is equal to 2 pi k rho naught. The integral of sine theta is negative cosine of theta, theta 1 to theta 2. We have 2 pi k rho naught. And because this is negative, we can simply say this is cosine of theta 1 minus cosine of theta 2. Okay, so now it's time to figure out what each of these cosine of theta 1, theta 2's are. So here, if I have the cosine of theta 1, it's simply going to be the cosine of 0 being equal to 1. So basically this is saying when my radius is 0, that means that the angle theta is going to be 0 as well. So cosine of an angle of 0 is simply 1. Now when I take a look at A, it means what happens to my theta, so this is theta 2, when I'm at my maximum radius A. So at the maximum radius A, the cosine of this theta is adjacent over hypotenuse. So adjacent is going to be, so cosine of theta 2, adjacent is z, and the hypotenuse is a squared, or yeah, a squared plus z squared. So all we have to do now is plug that in, and we have 2 pi k rho naught. Cosine of theta 1 is 1 minus z over the square root of a squared plus z squared. And we have forgotten the direction. And so just remember the electric field is a vector, so you have to have a direction in there as well. And now we are finished.